All right, let's start today's webinar. First of all, a warm welcome to everyone who joined. For the ones who don't know me, my name is Niels Verdijk and I will be your host today. Apart from being your host, I'm also a customer support engineer at Diabetics. So basically that means if you have any technical questions, you can always ask me. Okay, that's enough about me. Let's move on to today's webinar topic, which is generative design for a liquid nitrogen CPU cooler. Quite the mouthful. And as you will notice throughout this webinar, it is a bit of an odd one compared to our previous webinars. Let's start with the beginning, of course. Okay, going over the content. Let's start with introduction. I do see a few new names or names I don't recognize. So I will also do a quick introduction about our company. Then we will move on to the problem at hand, the liquid nitrogen cooling, and how it correlates to overclocking, or how overclocking can be solved by using liquid nitrogen cooling, how to optimize it using AI, and at the end of the session, we'll have a Q&A and quickly discover how to use Coldstream. This webinar, is scheduled for only 30 minutes, so let's try to do everything, to try everything and cram everything into 30 minutes. Throughout this webinar, as ever, if you have any questions, don't hesitate to put them in the chat box, either private or public. Our moderators are following both, so any unanswered questions or interesting questions we will be covering in this section. Should time allow for it, of course. All right. Starting with introduction about diabetics, of course. So as you all know, the power density or the power generated by electronic components or else are becoming more and more dense, which makes, of course, more challenging for thermal engineers to easily find designs that meet thermal requirements. And that's where we come in. We acknowledge that that is a big problem, and we want to focus on helping those thermal engineers by coming up with high-performing designs in an automated fashion. That's basically the core principle of our software, and we do this by giving thermal engineers access to very smart algorithms. On the top right, you see both ANSYS and Hexagon, the biggest names within the CFD world. They have acknowledged the strength of our software, have reached out to us, and as of recent, we made them our technology partners. Okay, but that's enough about diabetics. Let's delve deeper into what thermal engineers do today. So basically, from the design department, they will get some space to design a cooling solution. So they will first create a CAD model, first initial cooling solution, first initial heatsink, which they think, based on their previous knowledge, will perform very well. They will usually do either a CFD simulation or do physical experiments. And they will then analyze the results, basically, what is my temperature, what is my pressure drop between in and outlet. Usually, it's not sufficient, at least not for the first iteration. So they will then analyze if I change, for instance, a fin there or some material there. They will then analyze how those modifications will potentially result in a better design. And then they loop through this until they get a solution. So as you can imagine, it's quite a time-consuming process. And the amount of iterations that can be performed within a given time frame are limited, especially if the deadline is very, very tight. So that's where we come in with our generative design software, where the problem starts, of course, the process starts from the same initial problem, where you have some capability or some space to generate a cooling solution. In the first step, Coldstream allows you to, in a very quick way, generate a wide variety of concepts. Might very well be in a very short time frame. Might very well be that one of those concepts already meets the cooling requirements. Usually not, but it gives you a big or it gives the designer, the thermal engineer, sorry, already a very good understanding. If something changes to the geometry, how does that impact the performance? And the designer has then the capability to choose one of those concepts, to work it out in a more detailed matter, to get the most optimal solution for that application in, as I mentioned earlier, in an automated fashion. Okay, so how does the problem, or how does the internal design loop in the background look like? So on the left, you see basically the problem statement coming from the user. So you can basically request a given amount of objective functions. Let's say in this case only the one. Makes it a bit easier to formalize on the target on a slide deck. Let's say minimize the temperature of your heat producing component, which is then subject to a given amount of constraints, usually a pressure drop constraint, manufacturing constraints as well. So this comes then from the user, and then Sandstrom will basically use the initial condition, parameterize the geometry. We'll then perform a CFD simulation to know what the performance is of the initial condition. Evaluate it compared to the cost function. Does it meet my pressure drop constraint, for example, and my manufacturing constraints? And is the thermal performance sufficient? If so, then you basically have your design, so you can export it to CAD. If not okay, which is usually the case, the software has to perform a sensitivity analysis. What is this? So during a sensitivity analysis, the software will measure or will determine in what direction a modification to the design will result in the biggest improvement in your overall objective function. So after this sensitivity analysis is performed, the software knows which direction to take, so the design is updated, and then you loop through this until you are satisfied with the design, or the software is satisfied with the design. This all looks very easy, but in the background, of course, a wide variety of equations need to be solved, partial differential equations, like the governing equations, Navier-Stokes, energy equation, etc. But this is not the core, this is not the main thing that I want to cover here. So let's quickly move on. Okay, so now we have talked about the general ID or the general loop, the optimization loop that the software has to go through. There are multiple ways of tackling that problem. The easiest way of tackling the problem is by using parametric optimization. Basically, start from initial design philosophy, let's say pins or fins, and then you parameterize that design philosophy. I'll take the example of pins. We can parameterize the diameter of the pins, the height of the pins, the spacing between the different pins in both the X and the Y direction. And that's basically it. So with parametric optimization, your amount of variables is very much limited, which makes it very accessible, but you're stuck with the design philosophy that you choose a priori. So you will never get something that's very organic, very interesting looking. But it's an easy way of optimizing. Next, we have something called shape optimization, where you do have potentially some more organic structures that can come out of it. But with shape optimization, the software has to start from an initial design. Let's take this blob as an example. Throughout the optimization process, basically the algorithm has full control over the edge of that shape. It can redefine the shape. But that means, of course, that your final solution is very much dependent on your initial condition. So basically, the initial condition that your user dictates to the problem. Lastly, we have the solution that we at Diabetics prefer, which is density-based topology optimization. With density-based topology optimization, what happens in the background is your design domain, so the volume where you allow the software to make modifications, is split up in multiple small parts, and the algorithm basically has full control over where and where not to place material. Does the algorithm determine that, for instance, in this particular cell there needs to be material or not, or does it need to group material here in on this location or not? The software has full control over it. And by splitting the problem up in all of those different cells, the final solution is less dependent on the initial condition that the user defines. It can design something basically from scratch without any initial condition. Okay, so let's quickly showcase how that would look like on an IGBT cold plate. So where you basically have a stack of IGBTs on the top, some space below it to cool down, and then, oh, yes, and now you will see what the software will do in the background. So as you can see, it will add and remove material or reshape already specified material all along the solution space, the design volume, until it converges towards a final solution. In the beginning, you will have noticed that the design changes are that are a lot of design changes, while towards the end, when it converges towards the final solution, the design changes are only minor. It's basically fine-tuning of the design. Okay, and that's of course also what happens with Coldstream in the background. Yes, you might think this is a very difficult way. That might take a lot of time to learn how to do it, but it's not. You only have to follow 4 steps, which are laid out here before you on this slide deck. You have to start with, of course, uploading a geometry. The design that will come out of the software very much depends on where you allow the software to make changes. Basically, where does the heat come in? How does the heat correlate to the cooling solution, etc. Or the coolant, sorry. Next you set the solids and fluids. Is it copper, aluminum? Is it air cooled, liquid cooled? That of course all very much affects the final solution. Next you set the boundary conditions. Is it natural convection, forced convection? What does the heat load look like? That's something that you specify in step 3. And then step 4, that's a bit of a new one, especially compared to more conventional CFD software. You have to provide a design domain. As you know from the previous slides, is a volume where the software is allowed to modify the geometry, where it can basically add those optimization structures. And you have to let Coldstream know what the targets are, be it maximize heat exchange efficiency, minimize the weight, constrain the pressure drop. We have 20 plus targets that you can mix and match however you see fit. And that's it. So once you complete all 4 steps, the software will take over and will optimize the design for you. And once ready, you will be able to download results in step file format. A very big strength of our software, if I do say myself, is that you have, as a user, full control over how those structures should look like. Here are 4 of the most commonly used manufacturing techniques on the software: CNC milling, die casting, 3D printing, and sheet metal forming. And for each technique, you have full control over the settings that govern that technique. For instance, with CNC milling, you can specify what your minimal your milling tool size is. Basically, that dictates the minimal channel width. With 3D printing, you have control over the printing resolution of your machine, the overhang angle that your machine supports, as well as the unsupported lengths, both cantilever and bridge. So you can fine-tune those settings to meet your specific capabilities. So whatever Coldstream will output will meet those capabilities. All right, I think that's enough for the introduction about both diabetics and the software. Let's move on to the most interesting part, which is the liquid nitrogen CPU cooler. This is a project that we do in collaboration with Jon Sandstrom from ElmorLabs and Pieter-Jan Plaisier from SkatterBencher, the current 3 times world record holder for CPU frequency overclocking. So with decades of experience, both Jon and Pieter are known for their work utilizing cutting-edge extreme cooling solutions like liquid nitrogen cooling, like liquid helium cooling as well, on high-performance CPUs and GPUs. And this is also in a broader aspect, or in the broader range of something that we are developing for Coldstream. Okay, liquid nitrogen cooling and overclocking. Or now I will delve deeper into those applications. So how usually CPUs are cooled is you have your chip, there's a heatsink on top of it, and then a cooling circuit that goes through it. And the more the CPU has to work, the more the coolant has to flow, or the faster the coolant has to flow through it. You will have noticed it if you, for instance, run a very heavy program. Your computer can get quite hot. But usually those situations that you and I are familiar with, the CPU can do much more. So there's something called overclocking, where the speed or the calculations that the CPU or GPU can perform is dramatically increased. But as a byproduct, the heat production is also very much increased. And the conventional cooling solutions that I discussed a bit earlier, they simply can't keep up with the amount of heat production. So that's where liquid nitrogen cooling comes in. As you, I'm sure, all know, liquid nitrogen evaporates at nearly minus 200 degrees Celsius. So very cool. Very cool. And by using the boiling principle, you're basically stuck at that temperature. So with boiling, you basically start from fully liquid, and the temperature is fixed until everything is evaporated. And by using this, you can basically dramatically increase the heat transfer coefficient of your cooling solution. I hope that's all clear. The problem itself looks quite simple, quite easy. And how is it done in practice? You basically have a big container, like you have here, that's something that you put on your CPU. You fully fill it with liquid nitrogen. You run the CPU until everything evaporates away. So it's only for relatively short stints. There are quite a number of design difficulties, or difficulties during the design process itself. First of all, the problem is inherently transient. The cooling solution starts with a fully filled container, but the liquid nitrogen evaporates away. As with any cooling solution, in general, the more surface area that you have, the better the cooling performance. But, and that's a very big but, the evaporated nitrogen has to go away. If it's trapped, then you basically reduce the effectiveness of your cooling solution. So these two can go in opposite directions. And of course, liquid nitrogen operates at minus 200 degrees Celsius, or nearly minus 200 degrees Celsius. So the moisture inside of the air can condense, will condense at those temperatures. And if not taken into account properly, you will get issues with condensation on your CPUs. Okay. So yeah, let's cover now how we tackled this problem in Coldstream. The container and the design itself will be made out of copper. So very common for those applications. Makes the design also very heavy. We'll then put a temperature minimization objective to reduce to maximize the heat exchange efficiency, of course, while putting also a maximum relative volume of 20% on the design domain. This project is also in collaboration with 3D Systems, where we later on in the design process and in the project cycle, we will do physical experiments with that design. So we will take 3D printing into account as a manufacturing constraint, with the minimal printing size of 1 millimeter, an overhang angle of 45 degrees, and unsupported length of a cantilever of 1 mm and bridge of 3 mm. Okay, that's enough for now about the problem itself. Let's go to Coldstream to see how we set it up. Yes, you should be able to. Oh, okay, now it's back. So this is Coldstream, or this is the main landing page. After you log onto the software, and that's the project overview. So we usually use it to keep all of our different demos in separate project folders. But of course, if you have your own Colstream license, you can organize it however you see fit. I will go here. Yes. Inside of your project folder, you can then add cases. That's the engineering problems that you want to solve, where we support 3 types of cases. A simulation is just a regular CFD simulation, as you know it from other CFD softwares like ANSYS Fluent, like Gradle CFD. And then we have standard design and custom design. With standard design, Colstream is restricted to more conventional cooling solutions like pins, fins, generators, etc. And custom design, that's the full-fledged topology optimization, so where Colstream will turn a very custom design to your application. And once you create a new case, you then have to upload a geometry to that case. I will go straight to a case that already has that geometry. Simply selecting a step file and waiting for it to populate. And then you have in the middle here your geometry that you uploaded. And on the left here, you have the regions tree. Basically all the entities that were present within that step file will be parsed here. So as initial condition, we basically provided an empty container, so without any cooling structures in it, that sits on top of our CPU chip here at the bottom. We then fill it with liquid nitrogen, and our design domain is basically the same domain as our liquid nitrogen. We allow Colstream to generate structures everywhere. And once the geometry has been uploaded, you basically click on each of the entities and fill in the relevant information. So starting with our housing, which is of course of type solid, not a fluid. So I will select solid, and then it's made out of pure copper. Any settings below are optional. Then we have our liquid nitrogen, and here comes in, here I will delve deeper into the problem, or the way that we tackle this problem at this moment. So as I mentioned, the problem is inherently transient. The liquid nitrogen, the container starts with fully filled liquid nitrogen, and all of that nitrogen evaporates away. But the transient problem, or topology optimization at least, for transient systems is something that's not very well developed. So Colstream at the moment only supports steady state optimization. So to get around it, we will assume that the liquid nitrogen is a solid with the properties of liquid nitrogen, and our CPU is a binary condition. To make sure that, or in reality what happens is your CPU will be your heat producing component, and your nitrogen will be your heat sink. But if you set it up like that, we set it, our temperature of a heat source and a negative heat sink on the CPU, you will most likely get in the problem of negative temperatures, which are not realistic. So we flipped the problem around. And in this case, we will assume that our nitrogen produces the heat, and our CPU will act as our heat sink. So we basically invert the problem. Rather than having the heat from the CPU to the nitrogen, we have the heat from the nitrogen to the CPU. Seeing as it's a purely conduction case, that is basically the same. Or the heat path will be very similar. I hope my rambling made sense. And then of course on the liquid nitrogen, we want to minimize the temperature. So basically reduce the temperature, the thermal resistance between our CPU and our nitrogen as much as possible. And inside of the nitrogen, we allow Colstream to generate structures throughout the entire geometry using 3D printing. And again, copper will be used as a material. And as I mentioned in the slides, we restrict Colstream to only fill the design domain with at most 20% of the volume with pure copper. Okay, so that's the problem that we handed to Colstream. If I now go back here, we can have a look at the design solution that Colstream returned. So it basically filled the geometry with a lot of structures with a coral-like or with branching geometry. So you start here from all sides with thicker root, and then the structures will branch off. With the model that we used, especially with the nitrogen that will evaporate, the design will be very good in the beginning, but the further you are in the cooling process, the less effect these top parts will have. So this is purely a draft case for now. It's not the final solution that we will present. We will continue this this optimization process with different input. Okay, let's have a quick look at the questions. Oh, I'm also looking at the time now, seeing as we are quite close to the 30-minute mark. I will skip the questions for now. Of course, feel free to keep posting them. Our moderators will still answer them, but I will then move on to the final part, which basically delves deeper into where you can try Coldstream for your own. So we have a publicly available Coldstream. We have a public version of Coldstream where you can have a look at all the finished cases. So you can access it by utilizing or by following this link. Or if you want to know more about how Coldstream can help your company, feel free to email either at info@diabetics.com, or you can also phone the number that you see here. That's it from me. I hope you enjoyed the process. As I mentioned, this is the first part of a new capability that we are developing with Coldstream. So watch this space. There will be more content in the future. Okay, that's it from me. I hope you all have a nice day, and I hope to see you in the future. Bye bye.